This is the demo video for Group ME63. My project is to investigate a combustion rig's flame characteristics of liquid fuels as the flame nears blow-off or extinction. The fuels I am using are ethanol, toluene, and dodecane. This rig's flame is stabilized on the bluff body, which is the rectangular piece spanning across the cross-section, parallel to the long side of the rig exit. I am investigating pre-mixed flames, which means mixing the fuel with air before combustion. For optimal premixing, I am vaporizing the liquid fuel using an atomizer that shoots the fuel droplets of about 20 micron in length into a heated airstream. It is intended to analyze flames with average velocities of 5, 10, and 15 meters per second. Therefore, this fluid stream is turbulent. The airstream is heated to a temperature slightly above the fuel's boiling temperature, since vaporizing the fuel in the air helps in the premixing process. This is a 2-year project, and the objective for this first year and the senior design project is to get the rig operating with a liquid fuel flame. I updated the fuel injection system that sends the liquid fuel into the combustor rig. The fuel is initially pumped out of its tank by pressurizing it with pressurized nitrogen via a compressed gas regulator. Previously, a proportional solenoid valve was used to control the fuel flow rate, but there was a hysteresis with this solenoid valve. Hysteresis in this context means at a specific valve setting, the actual fuel flow rate saw differences depending on whether the valve was increasing or decreasing the flow rate. My replacement for this is a Dwyer variable area flow meter, which operates as a rotometer where the velocity head and the buoyancy of the fuel raises or lowers a float. The scale on the tube corresponds to a flow rate for water. Using the ratio of specific gravities between the water and the fuels, I developed a corresponding scale of fuel flow rates to the meter readings. After going through the flow meter, the fuel is then injected into the rig by the atomizer, perpendicular to the heated airflow. This atomizer has 3 prongs that blast the fuel into the airstream. There was also a need to implement a heating system on the walls of the rig to prevent fuel condensation. This addition is meant to ensure the fuel droplets vaporize in the airstream and react at the bluff body. This heating system consists of 3 components. There is a K-type thermocouple on the upper and lower section of the rig to monitor the wall temperature. These temperature readings are sent to an Omega temperature controller, which compares these readings to a temperature set point. Based on this comparison, the temperature controller signals the silicone heating tapes at the upper and lower sections to increase or decrease their heat release. These heating tapes are wrapped around the walls with about an inch or 2 of spacing between the next layer. The heating tapes and walls are insulated with an insulation blanket that is held together with wire. The next step to complete this year's objective is to check the bluff body for fuel droplets that do not vaporize in the rig. This can be monitored by creating a laser sheet of 532 nanometers over the bluff body and taking images with a solo PIV camera. This camera detects a light scattering called Mie scattering, which is from particles such as dust and in this case fuel droplets, whose size is much larger than the molecules of the gaseous fuel and air. If these images do not display these large fuel droplets, then that is how I will know that the heated air and walls are successfully vaporizing all of the fuel. The airflow entering the rig comes from a compressor whose pressure is controlled. Since it is of interest to run the rig where the average flow velocity is 5, 10, and 15 meters per second, I attempted to develop a calibration between the compressor's air pressure and the air velocity at the bluff body. I conducted constant temperature hot wire anemometry at varying compressor pressures to measure the velocity at the bluff body. Hot wire anemometry works by holding a 9.5 millimeter long wire with a platinum film perpendicular to a room temperature airflow. When air flows past the wire's temperature and resistance changes. This induces a voltage difference that is proportional to the fluid's velocity. The voltage change is displayed and outputted from the intelligent flow analyzer, which can be seen in the bottom picture. I measured the velocity at different pressure settings on multiple days where the daily high temperature varied by day. I noticed that even after running the compressor for half an hour before conducting hot wire anemometry, the temperature of the air that enters the compressor from outside impacts the velocity at the bluff body. Between days with high temperatures of 40 degrees and 60 degrees Fahrenheit, The average hot wire velocity at a given pressure setting differs by 1.75 meters per second. When I perform flame analysis, I will not immediately have a calibration curve at that day's temperature, so I will need to conduct hot wire at the beginning of that day to find the pressure settings for 5, 10, and 15 meters per second. This process would add about 20 to 30 minutes, but it would allow me to develop a master data set over that time that would then create a calibration for all the daily temperatures. By May of 2021, I should be finished aligning in OH-PLIF, FRS, and PIV lasers and optics. These will be set up to conduct filtered Rayleigh scattering and particle image velocimetry to simultaneously record temperature and velocity field data. I will begin this analysis with gaseous fields such as propane before moving on to my liquid fields of interest. After this, I expect to perform high-speed chemiluminescence imaging, which creates images of flame shape and intensity so that I can compare flames of liquid fields as they near blow-off. Thank you for your time.